Hi everyone, my name's Phil Winder, and I own my own consultancy that does data science and cloud native stuff. And today, what I want to do is try and provide some sort of antidote to the ever-increasing amount of technology and frameworks and information that engineers have to consume in order to do their jobs. It's split into three parts. I'm going to try and prove to you that your jobs as developers, you're actually becoming more and more like researchers. You're not really engineers anymore, even though your job title probably still has the word engineering in. Then I'm going to take a look at some great researchers and see how they did research, and hopefully try and pull out some things that we can then apply to our daily lives. And finally, we've got a little practical bit at the end where I'm actually trying to put some of the ideas into practice. So before we start, though, let's get some definitions and some terminology. Well, what is research? And actually, I apologize for the sort of layout here. I tend to wiggle about a lot, so I might end up doing this at some point, and you might not be able to see me, but we'll keep going. Research is about an attempt to improve or advance something. In science, generally, there is a more lofty aim of trying to improve the body of knowledge within the human race. But I would suspect that the majority of us are in industry. Can I ask can anybody put their hand? No, let's do it the opposite way around. Can everyone put their hand up if they're involved in industry? So all the academics, keep your hand down. Basically everybody. OK, as I thought. Yeah, my assumptions are correct, so I'll carry on. So in industry, the point of research is to try and improve or advance some process or thing for capitalistic ends, rather than a body of human knowledge. And the reason why businesses would do this in the first place is because, on average, any kind of research, any at all, has a positive return on investment. We're going to be a little bit careful about statistics here because the distributions are very wide and the tails are very long. So there's a few examples of 1,000, 10,000, million-fold increase in a return on investment. And also there's some negatives on the other side. But on average, throughout all industries in the world, 10 to 30% return on investment for any research performed. So that's generally why businesses want to take part in research. But I think there's more. There's something else to that as well. And on a more day-to-day basis, for people actually doing the work, I think that research and innovation actually breeds enthusiasm. So part of the problem in today's workplace, or at least maybe not necessarily today, but maybe 5 or 10 years ago, is that engineers' jobs were just by the fact that they were engineers, were very siloed, and you were employed to do a very specific job. And I tend to think that this locking down of people's potential it has an adverse effect, not only on their well-being, but also on the business at large. So let me try and prove to you that developers are actually researchers. So when we think about what a researcher is, then you would probably think that somebody that works in a university, or some sort of genius, some sort of person of historical importance that sits around on leafy lawns in the sunny sunshine under a tree, thinking up these new theories about life. And this is the first of many amazing pictures that you're going to enjoy from my artistic hand here. You can tell I'm not really an artist, but this is our general idea of a scientist. And that kind of breeds these misconceptions. Things like, I'm not smart enough, or I don't have a PhD, or only academics and people that actually have time to do research, that are called researchers, they're the only people that can do research, because that's not really my day job. And I want to prove to you that that's poppycock. It's rubbish. This is some research from Cambridge University, which aimed to provide some numbers and some metrics into the daily life of a researcher. I've got two charts. The first one here is an early career group researcher. So this is a guy that's probably just finished his PhD, is just going to postdoc research. And on the Y scale, we've got happiness, where happy is at the top and unhappiness is at the bottom. And on the X-axis, we've got time. So this is just one particular 24 hours of this person's life. It's color-coded. The green represents administrative tasks, red is teaching, blue is research, and gray is MISC. I don't expect you to be able to read some of this text because it's very small. But generally what I want to show is what research goes on during the day-to-day activities of an early-level researcher. And if we actually read some of these, I'll read them out to you. So the red tasks are teaching, marking supervision work, journal club, a bit unhappy here because one of his students hasn't read the paper properly. And then the things that is actually called research here. The things that is calling research are print out and read grant proposal, enter financial information for grant proposal, editing grant proposal, uploading proposal, and copying to laptop. So the things that he's terming research here is completely not research. It's like technical pre-sales. He's writing a piece of text to send off to someone to try and persuade them to give them money. And then we've got a bit more train home, supervising a bit more, Skype interview with a PhD student. OK, let's have a look at a senior researcher now. His day is a bit similar, really. It's interspersed with a lot of teaching. He's got some administrative tasks. Well, he's got coffee and lunch in there, which is quite interesting. Emails, et cetera, et cetera. And then the research that he's doing is grant proposal. Grant proposal. Oh, there's one here, writing an article on the history of ethics. So he has had about 30 minutes before he got a complaint about one of his courses, and it made him really unhappy. And the only time that he actually had time to write this article was between the hours of 8 and midnight. That's the only major difference between a low-level researcher and a high-level researcher, is the high-level researcher needs less sleep. So he can work until midnight and do more work at night. But throughout the entire day, he's doing very, very what I would call, very little what I would call research. As another example, this is a recent posting for a new lecturer position at the University of Manchester. And there's a couple of things I've highlighted: communication skills, interdisciplinary, policy, blah, 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 blah. The key thing I want to point out is the focus of the research must be in one of the following areas. So the universities and the deans of the universities are saying you have to research on a very specific topic. So it's often not this free-thinking, open research that these people do. They're usually doing it to a very specific target market. And you also need a track record in publishing, a little bit of teaching experience, but it's not really that important. And the most important thing, attracting research funding. So basically, what they're asking for is somebody that can do as they're told and get lots of money. It's a little bit depressing. But in summary, these guys have specialist knowledge, and girls, sorry. These people have specialist knowledge. They have some experience in teaching, but not necessarily any qualifications. They do a lot of administration, lots of meetings with other students and people, lots of sales, and a little bit of research at the end. Now, what do we do on a daily basis? We have specialist knowledge. We've been to university. We've learned how to perform our craft. We are probably part of some sort of mentoring scheme, either we're the mentor or the mentee. We do a lot of administration. We spend a lot of time on Slack. Anybody? And we have meetings that we don't really want. And finally, a little bit at the end of the day, we do some software engineering. Our jobs, our roles are exactly the same. So let's go back to what is research again. It is the pursuit of knowledge. It is to develop a new understanding, a new generalization, a new theory, and then deliver or enact upon that theory. In an engineer's daily life, we do this every day, every minute, every second. In the pursuit of knowledge, we come up against a problem, and we ask the question, why does HTML think Chuck Norris is a color? And it turns out that in the HTML spec, Chuck Norris is actually a valid color. It is a red color. Now, at this point, we start thinking, OK, we need to develop some new understanding here. What on earth were these guys thinking, putting the word Chuck Norris in the HTML spec for a color? And it usually involves some sort of face palming, something like that. And then we need to deliver this new knowledge. What do? We refer to our old friend, copy and paste. So this is on a daily basis. We're doing this kind of research. So if we accept for a moment that we are disguised researchers, then what can we learn? What can we do to make these things better? So there was a chap called Francis Crick, who is a British biophysicist, and he's most famous for discovering DNA. And he discovered DNA in about 1953, and he got the Nobel Prize in 1962 with James Watson and Maurice Wilkins. And this is all quite well known, and he was a very incredible man. But the really interesting story for me is the background to this. It's how did he actually get to that point? And when you actually look at his background, it turns out that he was actually very sort of normal and average. He was born in 1916, and he was lucky enough to be born into a reasonably wealthy family. And his uncle, who was a rich businessman, was able to pay for him to go to school. Because, I mean, especially, well, maybe in London people started going to school at that point, but especially in the north, you know, generally people still didn't really go to school at that point. And he went to school until the age of 16, and he was then expected to go to university, but he actually couldn't get in anywhere. He couldn't get in. And so he got accepted in what was then it was known as that godless college. It was University College London. It was one of the first secular colleges in the UK. And he got accepted at UCL, and he did a physics degree. After this point, he then persuaded somebody to let him onto a PhD. Oh, he got a second class, by the way, a second class degree. And he persuaded someone to start a PhD, and about 2 years into his PhD, World War II broke out. And unfortunately, one of the bombs that hit London landed on UCL and blew up all of the laboratories and the workshops, thankfully at night. But what it did is it totally destroyed all of the experimental apparatus that people were using to do research at that time. So it meant that nobody could do research anymore. So they all stopped, and they went to the Admiralty, and they worked on military tasks. And actually, it was there that he began to gain a reputation for working hard. And that was really the only reputation he had at this moment. And in fact, a lot of people found him quite annoying because he spoke too much. He just kept talking all the time. When the war finally finished, he got back to his PhD, and he finished his PhD when he was 32. So the end of his academic, you know, his training was at 32. He didn't start doing anything until he was about 32. Then, by chance, he got offered a postdoc, and he started getting interested in biology, and he met a few people. He met James Watson, and the rest is kind of history. But it took, you know, more than 30 years before he could actually start doing any real work. And looking back on his life in his memoirs are really interesting, because he said that he recalled going home and telling his wife that he's got this new amazing thing, you know, this new amazing JavaScript framework that people are really interested in, is really sexy, and I'm really excited about it. And his wife said that you were always coming home and saying things like that. She didn't really care. She didn't think DNA was a big deal. And even to the point that that Francis Crick was talking so much about this and getting so enthusiastic that James Watson, he soon actually began to worry that they didn't really have anything at all. They thought it was all a pipe dream. And so after a couple of years, they stopped, and they had another big look at what they were doing and all of the new research that came out. They did a full iteration. They basically nearly cancelled the entire thing and started again. And they found that they'd made a load of incorrect assumptions when they started. And through that iterative process, they finally got to some fundamental properties of DNA. When he tries to sum it all up, he says that he enjoyed the downs as well as the ups. And I think that's because that is the story. That is the story of his life. You know, the bad parts as well as the good parts. And you know, it's like engineering. The important thing is to be there when the product is being engineered, because otherwise you're not part of it. You're not creating something. It's the creative process that defines who you are and how you live your life. And when asked, okay, well, how did you actually do it, seriously? Because you didn't really start until you were 32, and now you're this world-famous dude. He basically said that it was just partly luck, partly good judgment, inspiration, and persistent application. And that was the key character of Francis Crick, was this persistence. He kept working when everybody else thought that he couldn't work. But other people actually said another thing. They said that his genius was collaboration and conversation, because a lot of his ideas were only born through conversing with other people and talking to other people. If he was left to his own devices, he probably wouldn't have done half the stuff that he did. It required other people to bounce ideas off. So, based upon Francis Crick, the best researchers are confident yet humble, critical and collaborative, ambitious yet realistic, thorough yet they know when to stop. So we can expand upon this and actually start thinking about some of the qualities that engineers and researchers need in order to do their jobs well. And this is intended to be the first little bit of practical advice that I'd like to give you. Again, I don't expect you to read the text, it's too small, but take a look at the slides afterwards if you're interested. I've split this up into 4 main quadrants. We've got technology, business knowledge, and internal and external qualities. You'll see that the technology segment is only about 1/4 of the image. And that's because I believe that technical ability alone doesn't really make a good engineer or a good researcher. Most of the brilliant engineers that I've ever worked with have been people that I can communicate with, essentially, talk to, work through problems. They're there to help, and things like that. And often the solutions that they come up with, these brilliant engineers, are really simple. And it's that simplicity that cuts through all the technical BS. But also, business is a huge part of industrial research. If you're not aware and you're not involved in the business in terms of being empowered to make decisions, essentially, then there's a significant amount of you that is not exercising your full potential effectively. You can affect and direct a business by your actions. You should know about it. And then we've got internal and external qualities. So internal qualities are things like passion and persistence. And especially persistence are one of the key tenets that I really appreciate. And then external. There's so many really great engineers here that are just either embarrassed or afraid or too scared to just talk to people and talk about their work. And not exaggerate themselves or be arrogant or anything, but just to communicate with other people. And you'll find that other people will be massively impressed with your work. And you might even find other people helpful. So the idea is, if you go and have a look through this, if you find some of your positive points, then you can try maybe reselling yourselves in terms of those positive points. Maybe you can stress that you're really good at these things. If you find some negative points, maybe it's something you should try and work on to make yourself a better engineer. So let's have a look at some more step-by-step practical advice. I'm going to slow down a bit as well because I'm talking too fast. So hypotheses are the root of all that is science. A hypothesis is a proposed explanation which is usually based upon prior knowledge or background knowledge or preliminary results, things like that, and logic, to describe some phenomena. And hypotheses are generally quite abstract in the things that they're asking. They may not be very specific, and they're sometimes some of the best questions. And the whole goal of research is to try and find data or information that will prove or disprove that hypothesis. And this is the basis of the scientific method. It's a systematic observation, measurement, and experiment for mutating hypotheses, effectively. And there's actually quite a well-established way of doing this, of doing research. And I think this is a little complicated, so we'll simplify it in a little bit. But it's effectively the same thing. We first make some observations and think of some interesting questions. So it's like, if you are accidentally working on something and you notice something interesting, you're normally saying things like, or what the fuck, or again. And it's those kind of things where you're starting to formulate, it's those times where you're starting to formulate these interesting questions, and they are the basis for hypotheses. So once we've formulated some hypotheses, then we actually need to develop some testable predictions. And this is really the only way that that hypotheses can be proved or disproved, and that's if you have some way of testing them. If you can't test them, then to be honest, they're a little bit useless. You need to reformulate your idea in order to make it testable. Then we need to actually perform some experiments. We need to gather some data. And then finally, if we've done all that, we can do some evaluation, refine, improve, alter, expand, reject, hypothesis, and generate some general abstractions. So you might be thinking, okay, that's all well and good, but how does that apply to software engineering? So let's go back. I'm going to keep using this example because it is really simple, and it's something that everyone does on a day-to-day basis. But we've got a chap here, and his name is @slide34, and he's an engineer. And you can tell that he's an engineer because he's got an @ sign before his name. And also, he's got hair in the wrong places. So he's got hair down here rather than on his head. And so you can easily tell he's an engineer. And he has a bug. So this is his code, and it's not working. When he runs it, it comes out like this. The idea is he's got some flag. When he sets it to false, it shouldn't do some work. Yet, it is doing some work. So the first thing that we do is go, what? Hey, what the hell? And because he doesn't know what's going on, he's actually quite confused at this point. So he takes a step back, and he asks some questions like, OK, well, I don't expect this to happen. What do I expect to happen? I need a hypothesis. I need an interesting question. So the problem is that my code's not working. My hypothesis is I don't really have one at the moment. So I'm just going to keep plugging away and generating a bit more data so I can then make a proper hypothesis. What we normally do is we just start inserting random debug statements just to see where the code has got to. And I popped in a little debug statement there. Hello. And that is our first testable prediction. Does this print? OK, then we run that, and it's blank. And he's like, what? Seriously? Who uses C++ anymore? Yeah, it's that idiot that chose to use C++. It's his fault. And after he's had some swear words of various things that we can't print, he calms down, and again, he answers the same question. OK, well, that didn't work. We need to refine our hypothesis. What can we do? And then he notices something. He notices this little slash. He's like, hang on. What's that slash doing there? And he's like, the standard out is ignored. Is it that slash? Yes, I think it's that slash. So our new hypothesis is this trailing slash is actually just creating a new line for this comment. And so our hypothesis is if we remove that slash, our code will work. So this is our new testable prediction. And then we've got our hello world at the output. And in this case, the engineer is now very happy. He's doing a bit of a fist pump. And he's probably got very strong biceps because engineers are doing this, this a lot. And that's generally why I love engineering, actually. It's because there's so many of these through the day. It's all of these little tiny little successes, these times when we win. They're really, really satisfying. And the general theory in this case is I'm an idiot. Or the person that chose to use C++ was the idiot. But whoever, somebody is an idiot because they made a silly mistake. And that kind of research has got a name. It's called experimental research. And it is performing controlled experiments to verify a hypothesis. Some of the key features of experimental research is that we are performing tests to provide a comparison between differing designs. So in this case, we're just changing the code a bit, and that becomes a new model. That becomes a new thing that we're trying to test. And we're doing a comparison to see whether we can achieve our testable metric. The issue with this style of research is that it requires a robust metric. Now, in software engineering, that's kind of OK, because usually it's quite robust. Your software does work or it doesn't. It's a very robust metric. If it is, then it's working. If it's not, then it's bad. In other domains, and maybe even in your domains, the solution might not quite be as clear-cut as that. Depending on repeatability, it may require lots of data. So experimental research requires lots of data to make sure that your result is significant. That's a statistics term. So for example, if we've got a flaky unit test, for example, in our CI pipeline, it may only fail one in 10 times or 1 in 100 times or something. So we need to be able to run that test hundreds and hundreds and hundreds of times to be able to make sure that we've found that bug and fixed that bug. So yeah, experimental research. And stepping back a little bit to the start of that that process, it can actually often be quite hard to start doing research. So it's like, where do I start looking? How do I do it? What do I do? And it actually comes back to something much simpler, something you learned in like primary school even. And these are like the journalistic, 5 commandments. It's the what, where, when, why, how. And that really helps when you're starting research. So for example, what is the research? Why do I want to do this? Why am I doing this? What's the point? Who are the participants? Who is it going to affect? What is going to be affected? Where can I perform the research? Is it something that I can do on my laptop, on a server? Do I need a big cluster? Is it not even anything to do with software? And when am I going to do it? Does it make sense to do it now? Are there other more important things? So yeah, what, where, when, why, how. But on top of this, the why is really important. And I find this is one of the most useful tools, actually, when starting a project. Because one of the biggest reasons why projects fail is because you don't understand what the client or the customer or the business actually wants. So I had an experience early on in my career when I just left university. I just finished my PhD. I thought I was super cool, and I thought I knew everything. And I went into this business, and I worked really, really hard. I worked my ass off for I think it was like 3, 4, 5 months. And after those 3, 4, 5 months, I had like a performance review. Performance, it's a stupid name, but they pulled me into the office, and I was super happy. I went in with a massive smile on my face because I thought I'd done really well. I'd done exactly what I'd been told. I'd done it well, and I'd done it efficiently. So I was really happy. And they came in with quite sad faces, and I was a bit worried at this point. And when we started talking, it was like, yeah, Phil, we've got a bit of a problem. So basically, you've been doing the job of a software engineer, and they actually used the term software engineer. I was like, okay, it's a bit offensive, but all right, let that slide. So we're going to have to actually reduce your pay to a software engineer. And I'm like, what? What the hell? What? So firstly, you've been telling me what to do all of this time. And they're like, yeah, I know, I'm sorry, but when we employed you, we expected you to kind of overhaul all of the algorithms that we were using. I'm like, what? When did you tell me this? It's like, why? And I kind of blamed them at the time, and I was quite mad, and I was really upset by it, because I hate being told that I've done a bad job. That's like the worst thing you can say to me. But at the time, I was really upset, and I blamed them a lot. But over time, I kind of realized that it actually was partially my fault. I didn't actually ask them, why am I here? What do you want me to do? What's the point of doing this work? What are you expecting out of this? I didn't ask those questions because I didn't have the confidence at the time. I thought they were the big bosses. They knew what they were doing. And they were the ones that were telling me what to do. So ever since then, I've always asked why. Why do you want me to do it? Yeah, but why? Well, we want to make the product better. Yeah, but why? I said, well, it's kind of losing us a bit of money. It takes too long to tune these algorithms. Yeah, but why? Well, I don't know. That's how we make our money. So we need better algorithms. Thank you. There you go. It takes 5. I think it came from lean manufacturing originally, from Toyota, and they advanced this idea of the 5 whys, and it really does work. And it works so well that actually I thought I'd do this. It would be quite funny just to provide some comic respite after that sad story. I went into Google and I typed in why are, and then I typed in an occupation, so. And then blank. And I let Google autocomplete the next part of that word. So the answers to all of these questions are, why are engineers so boring? Why are software engineers so arrogant? Ooh. Why are electronic engineers so weird? Why are mechanical engineers so little? That is actually the strangest result I saw throughout the whole thing. Who is asking that question? Why are politicians so old? Why are managers so mean? Why are bosses so rude? And the best one, why are people so stupid? Cracking. And that's a good interpretation of what the rest of the world is Googling about engineers. I thought I could only talk about engineers and politicians because I thought if I offend you, yeah, it's okay. You can always punch me afterwards. If I offend politicians, that's great. But if I offended anyone else, then I'll probably get told off. So yeah, okay, move on. So what I found, really, the root cause of everything, when you ask those 5 whys, the reason why you're doing a job in the first place is to do one of these things. Again, we come back to capitalism, where the business is either trying to make money, reduce costs, or save time. It all comes down to money eventually. And I would say that pretty much all of my experience has been this. I'm not saying that's 100% of all work, but the vast majority of work that we do comes down to money. So if you can propose or come up with ideas that achieve one of these goals, you're in a very good position to be able to do effectively whatever you like. And this comes back to action research. So action research is a slightly different type of research where you already have a problem or you already have an idea. And the whole goal is to make it more, is to optimize it to the point where you can make the outcome more desirable. It usually relies on having a purpose. So the purpose can come from the business, from your clients. Maybe it's your business. Then we need to focus on the problem and generate these hypotheses, and also keep in mind how this is related to everything else. Does it have any relationships with other parts of your system or product? Does it have any impacts on people? So I work in data science quite a lot, and even more so than software engineering, there's a real problem that the things that I do and the products that I create are automating manual tasks, which usually means I'm basically trying to, make it easier for a computer to do the same thing as a human, which has the knock-on effect of that human's not necessarily required to do that process anymore. And at a lower level, that's what software engineering tries to do as well. But that has a massive impact on how I do my work and how I present it. Then we need a method to actually achieve that. And finally, we need to validate that we've actually provided some positive impact. And I think we can simplify this to what is effectively the OODA loop. So look up the OODA loop because it's quite interesting. But effectively, it's trying to find a problem, understand a problem, solve the problem, and then review. So let's go back to our bug example again. I promise you I'll get off the bugs in a minute. So first we need to find the bug, and quite often that comes from customers or other people, and you don't really understand it, and you don't know why it's there or how it works. So we need to first inspect. We need to learn about the bug to be able to understand it. And after getting our magnifying glass out, we found that little bug was actually a banking bug. And in this case, you can tell it's a banking bug because he's got a bowler hat and a little tie, and it says bank on his briefcase. And whenever we're trying to solve bugs, we're trying to get rid of them. And a lot of people would like to get rid of quite a few bankers with a hammer. So we take a hammer and we squash the bug and we fix it, and it's all done. But then we need to go through some sort of review phase to figure out whether that carcass of the bug can be found somewhere else in the system, or possibly it had a negative impact on some other part of the system. And so on. So you might end up going around in circles, fixing bugs after you've just found that one individual little bug. So let's take a bit more of a realistic example. So bug fixing is something that everyone does on a day-to-day basis and everyone can relate to. But the whole point of proposing research as a new way of doing work, there's obvious business benefits to it, but what about you? What about the people actually doing the research? Why do I find it interesting? And I find it interesting purely because I like learning about new things. And the issue is that it's sometimes okay to say to a business, I want to learn new things, because it will have knock-on effects to the rest of your day job. But ideally, what you want to do is to pose your learning as a direct benefit to the business. So rather than saying, I'm interested in learning this new JavaScript framework, again, which is what you did last week and the week before that, instead, try and reframe the problem in business terms. How will it help? What will it affect? Think of saving costs, saving time, making more money, those three things. And so we could change it to, we want to improve front-end developer productivity. And that might reduce lead times on new features. And that's great, and that sounds much easier to digest from your boss or your client and basically the person that's going to be paying for this work. But the key questions are, why? Again, why? How long and how much? Once we've kind of figured out them a little bit, we need to take those initial statements that we came up with and start to pull them apart. You can really be very critical about the words that you write down. And it actually might take you quite a long time just to get to this sentence, this one thing. So we've got this definition of developer productivity there. What do we mean by productive? How are we going to measure productivity? Is it in terms of features, in terms of fewer bugs, in terms of time? I don't know. What exactly we're going to be testing? You can't just say we're going to look at all front end. JavaScript frameworks because you'd be there for 10 years going through all the various options. So be specific. So once we've defined what productive is, how are we going to measure it? And how are we going to measure lead times for that fact as well? What metrics do we need to be able to measure that? And really importantly, we need baselines. Without baselines, so a baseline is like a measurement of a metric effectively before you've done any tweaking, before you've done any optimization. There might be some natural baseline, like if you're just randomly flipping a coin or something like that. Or maybe you've tried things in the past and you've already got some information about some of those metrics. But baselines are really important. And who does this affect? Does it just affect front-end developers, or could other people get any feedback from this? And actually, the middle bit, the solving, the bit that you think of as your day-to-day job, it's actually kind of the easiest bit in my experience, because there's already so much literature around this. This is all the agile stuff. This is all the development. This is all the how to do X in Y. You can use all of that to solve your problem. So I'm not going to talk about that. And then finally, the review phase is really important, because that is where you get to show off your work. This is where you get to prove that you have done what you said you were going to do, and also implement any actions that you find. For an engineer, publicizing these outcomes is probably one of the most difficult things, because maybe you're just not used to it. It could be something as simple as just sending an email. But generally what I would try and say is, if you can visualize it, if you can get something visual, it's much easier for everybody to interpret. And they will appreciate what you have to say. They will appreciate the image rather than what you have to say. And then we need to repeat or bail out at the end of that loop. Often we keep repeating and keep repeating. But sometimes we have to bail out. But how do we decide that? How do we decide to bail out? There's this idea that, again, has kind of come from lean engineering stuff, Toyota stuff, to fail fast, to fail as quickly as possible so you don't end up wasting money on things that you don't need. And I think the idea behind it is sound. It's OK to think that, but I think it can be interpreted in the wrong way. I think what I see sometimes is that you know when you sit down in front of your laptop with a new problem, and there's an overwhelming sense of, it's like a siren sat on a rock. It really wants you to start coding, just to hit the keyboard and start coding. It's really alluring to just get into the problem and start coding without actually thinking about it. And then after some time, the problem becomes sort of diffused, and the other problems crop up. And we use this idea of failing fast to disguise not doing our job properly. And I think this doesn't just apply to us, obviously. It applies to business as well. I'm sure that there's lots of businesses that have had the plug pulled by venture capitalists or whoever before they had the potential to actually fruit. So instead of failing fast, I like the term stop smart. I haven't heard that before. I think that's my own idea, but it's pretty silly. But stopping smart has a much greater impact on yourselves, the business, and the users, or the public more generally. So to describe this, I like to talk about the perfect product. So how do we define what a perfect product is? And this sort of alludes to minimum viable products in a way, but it's the idea of not quitting too early, because if you quit too early, you'll never have the perfect product, but also not quitting too late as well, because any excess work that you perform to try and make your product better is just not going to make it better. There's just no point. It's a waste of your time. So we need to try and bail out exactly that point. But that is actually really hard to do, because it's really hard to define how perfect your product is. Some ideas could be maybe revenue, yearly revenue, maybe some technical measures, features per week, something like that. And what we're aiming for is something that looks like this. Over your career, over your lifetime, what you're trying to do is to create these products and stop at that peak, because you don't want to keep working and keep thinking like you're adding value when in reality you're not. And at the same time, you also want to keep going. You need to be persistent in order to reach that flowering point. Each of the things that you do, each of the products that you're involved with will have different absolute levels. Some will be more successful than others through no fault of your own, just purely down to the market. But still, I think it's our responsibility as engineers to make the best thing that we can. But one of the issues I see is that people tend to get bored very quickly, especially engineers. Like, this is probably the reason why there's so many bloody JavaScript front-end frameworks. If some of them just actually got together and started just persisting and continuing with what they've got and improving what they've got, they'll probably end up here somewhere. But in reality, React will always stop halfway down because people get bored of it and move on to the next thing. So that's bad. That's bad for you because you never get to do your best work. It's bad for the business because they're not extracting all of the profits that they could. And it's bad for the customer. They're not getting the best thing that they could. And then there's the opposite. It's continuing too long. If you continue too long on the same project, you encounter this thing called a sunk cost fallacy. And that's basically the idea that you've spent so much on your thing already, it's really hard to bail out. I feel bad for one of the guys in the front row because the cameraman has just been staring at him for like an hour. He's got his picture now. And sorry, I get put off by cameramen. It's quite funny. The sunk cost fallacy causes products to kind of continue for longer than is strictly necessary. The customers are no longer getting any value out of it, and the people are getting bored. And how do we achieve this? How do we actually measure this? Well, this is where data science comes in. And there's a specific subdiscipline of data science called analytics. And analytics is the idea of trying to guide the business and the people to make better decisions. So we start off with a testable hypothesis. Again, this is just research. And we need a robust metric if we can. So like, is the program running or not running? It could be total revenue. Revenue is always a really good one because it's one of the true measures of a business. But you might not be so directly coupled to the business itself. So it could be something like the number of active customers or an error rate if you're going really low. If you're building some high-performance system and your business depends on being high performance, then the error rate could be a good metric. Once we've got the testable metric, the testable hypothesis, the thing that we're trying to test, then we need to try and develop new metrics that explain that final metric, but not in that form. Things I see that are usually quite good metrics to predict how well a product is doing are things like empowerment. So like how happy are the engineers? Do they feel empowered to be able to make decisions and enact the things that they believe in? Performance, obviously, if we can establish some sort of performance metric, I don't know, like number of new features. This is kind of all of the agile, metric type stuff that people have been talking about in agile. So number of new bugs, number of bugs fixed, number of new features per iteration, things like that. But a key one that doesn't often get talked about is buy-in from stakeholders. So if your stakeholders, whether that's your client or your boss or just somebody who has a controlling stake in what you're doing, do they believe in what you're doing? If they don't believe in what you're doing, then it doesn't matter how well you work, it's always going to end badly. So if you can develop some metric to measure stakeholder buy-in, I don't know how you do that, that's actually a bit of a hard one. Maybe it's the number of times that this stakeholder views your dashboard. Maybe it's the number of emails it's sending about your product a week. Something crazy like that. And finally, does it align with the business? And is it successful as a business? Is it making money? Does it make sense? Combining all of these things, we can generate some real predictive benefits. And then this is where data science comes in. So given our hypothesis and given our data, can we find any metrics that have any predictive power? What are the key performance indicators? Can we visualize the results and report the findings? based upon all of that information, take some action. If you don't take any action, then the work that you've just done doesn't make sense. You haven't achieved anything. So are we collecting the best metrics? Are there better metrics that we can improve? Can we perform some sort of test to try and improve some of those metrics? So we can start doing, well, yeah, I don't need to go into details because it's been discussed quite a lot already. Do personality traits correlate with those metrics? That's a really interesting one. So is persistence something that's directly affecting your business? If so, you might want to try and start rewarding persistence somehow. I don't know how you'd do that, but you can find that some personality traits correlate well with the business goals. And finally, baselines. Do any of the things that we've learned represent any new baselines? The one tricky thing in all of this is actually timescales. So it's quite easy to imagine that we can get this data, but one of the biggest problems with the data is that it belongs on different timescales. So things like new bugs or new features or something, they're on like a sprint level life cycle. So they're updated maybe once or twice a week, something like that. Things like business metrics are only updated maybe once a month. So you've got these different timescales that you need to play with. So one of the best ways that we can overcome that is by doing some more data science to perform some regression on some of the longer-lived metrics like business metrics. And then we can predict, sub-cycle metrics if we need to. And I think about bang on time. So I think I'll stop there. If I was just trying to summarize all of that up, all of what I've just been talking about, is I like the analogy of gliding. So if you've ever been in a glider and you try and pull up and force it into a stall, then you actually feel it. You feel it in the plane starts to shake, you feel it in the controls start to wobble, you can see the indicator, the airspeed indicator drop to 0, and then you obviously fall back to the earth. When I'm working on projects, you can sort of see rumblings of that in real life. I start to see people leaving the company. I start to see people complaining about the managers. I start to see issues with direction and things like that. So if we were to try and think of this like intuitively, think of it like that. That's when you should be thinking about bailing. OK, so yeah, my name's been Phil Winder. I'm a data scientist at heart. If you're interested in any of that, then come and speak to me. Thank you very much. Goodbye.